Welcome back to module 6 of the course time dependent quantum chemistry. In this module we are discussing analytical methods to solve TDSE. There are two ways one can solve TDSE. Of course, one analytical method and another one is numerical method, but most of the solution will come from numerical methodology. However, there are very few analytical methods available to solve TDSE. One of them we have already understood. It is time dependent perturbation theory. Next, what we will be going over is called quantum adiabatic theory. In this to present this quantum adiabatic theory, we will make use of the particle in one dimensional box problem. If we present the quantum adiabatic theory along with this example of particle in one dimensional box, it will help us understand the fundamental principle of this theory, adiabatic theory, very easily. So we will begin. We have already realized that the solution to the time independent Schrodinger equation provides a set of stationary state wave functions represented by psi n. So if I have this time independent Schrodinger equation, which is given by this, we get actually, so when we solve time independent Schrodinger equation, we get the entire spectrum of the system, which means eigenstates of the system, and the nth eigenstate, let's say this one is the nth eigenstate, and that eigenstate can be has an inner eigen the wave function psi n and its energy En. That's the energy, and that's the way we get, that's the entire spectrum of a quantum system is obtained from the solution of time independent Schrodinger equation. As an example, one may consider the classic problem of particle in one dimensional box of length L. So this is what we have, the example 0 to L length we have, and this problem is also known as particle in infinite square well potential. The stationary state, the nth wave function, the nth wave function, stationary state, of course these are all stationary states. They are stationary states because, not because wave function does not have time dependence, but its probability density is time independent. That's why it's stationary state. So all the stationary state solutions we get from time independent Schrodinger equation, and the nth wave function is given by this expression, the expression which is very well known to us, because this is a very frequently taught problem in quantum mechanics. And the energy states are following. The first energy state is having energy this one, the second energy state having energy this one, and we go on like this way. So when we represent the stationary state wave function of the particle in one dimensional box, here n can be 1, it can be 2, it can be 3, this is the quantum number, and it can go up to infinity. So all states can be explored from this wave function. When we express the wave function following using this form, we assume that mostly we probably haven't noticed it, but we assume that the length, this L term in this equation, remains fixed. In fact, the L term acts as a parameter in this equation. This is why the nth stationary state wave function of the particle in one-dimensional box should be more appropriately represented by this. We can use x, then semicolon, then L equals square root of 2 by L sine pi x n by L. What we are doing here to define the notation of this wave function, what we have used is that we have used L as a parameter, and anything we are writing as a parameter will be separated from the variable. Variable is the x coordinate here, the position coordinate is the variable, but the parameter is separated from the variable by a semicolon. That's the convention we will follow. So if I have two parameters of a two variables in a function, let's say x and t are variables, they are separated by comma. But then the parameter, if I have a parameter in it, so it will be separated by a semicolon. That's the convention we will follow. So if we have, so more specifically, this is not done very quickly, very frequently in the textbook, the popular textbook, when we represent the one-dimensional box problem, because it is assumed that L is constant. But more specifically, and with regard to the presentation of quantum adiabatic theorem, we will actually specify that this wave function parametrically depends on L. If I change the L, my wave function will change, but it is not a variable, it is parameter. So if I have these wave functions written like this, then the time dependent wave function, as we know, this is time independent part. So time dependent wave function can be written as follows. I have nth wave function as x comma t, then parameter is equal to square root of 2 by L, then sine pi x n by L. Then I have this time dependent phase factor, which is e to the power I e n t by h cut. So that's the way we should represent more. We can maintain the notational accuracy with the help of this, where En denotes the energy of the nth stationary state of the particle. So what we see from this expression is that the time dependence comes entirely from, and this is the way, this is what we have, this is a concept which we have developed so far, that the time dependence comes from this time dependent phase factor. Time dependence of the wave function comes from this time dependent phase factor, and this is what we have developed since module 1. Now in all the hitherto treated time dependent problems, we have assumed that the parameter, what was the assumption we have made so far? Always the parameter which defines a stationary state wave function for example, here it is the L in this example, and that's why we are, when you will be representing quantum adiabatic theorem, we will be giving an example so that one can directly connect the meaning of the mathematical expressions or the statement which we are making. That will be that this will make our learning process very easygoing. So so far in all the treatment, what we have done, time dependent treatment, we have assumed that the parameter which defines the stationary state wave function does not change as a function of time. This is the assumption we have made. So the time dependence term in the wave function comes entirely from this phase factor. This is what we have seen. On the contrary, when we are presenting this quantum adiabatic theorem, we will say that this part is not right. We will say that quantum adiabatic theory, which is the subject of the current discussion, it will try to find an answer to an unexplored question. The question is following. Question is, what will happen if the parameter which defines a stationary state wave function changes very slowly as a function of time. So in time dependent perturbation theory, when we have employed time dependent perturbation theory, we have assumed that the stationary state, the parameter which is defining the stationary state, is not changing. So entire time dependence came from the time dependent phase factor. But on the contrary to this picture, when we are presenting this quantum adiabatic theorem, this is also another dynamical evolution of a quantum system. We are saying that we are asking this question, that what will happen if the parameter which defines a stationary state wave function changes very slowly. So one approximation is that the change has to be very slow. The parameter which is changing has to be very, very slow. Then we will be able to explore this quantum adiabatic theorem. If it is fast, then we cannot explore quantum adiabatic theorem. But if it is slow, then it is good. So quantum adiabatic theorem is actually based on an approximation that is called adiabatic approximation. Adiabatic approximation assumes that the parameter is changing very slowly. So our target is not time dependent phase factor. Our target is actually the parameter which is changing as a function of time very slowly. And this slow temporal change, this is an approximation in quantum adiabatic theorem. This is called quantum adiabatic approximation. Quantum adiabatic approximation. So we will, under this approximation, so if we connect it to our example, we'll say that at time t equals 0, initial time, the length was L0, and it is slowly changing, expanding the box, and at time t, the final time is t, so the duration of the adiabatic change, of, when I say adiabatic change, it is a slow change. Adiabatic change is 0 to t during this time, and the aim of quantum adiabatic theorem is at exploring the wave function after the adiabatic process is turned off. So that's the problem we have at hand. The Hamiltonian of a particle particle in one dimensional box of length L, let us say, is given by this. We have kinetic energy and the potential energy. I have deliberately given potential energy term here because although generally this is we write as 0, because particle inside the box the potential energy is 0, outside the box potential energy is infinite. So that is why we make it 0, but we cannot directly write down 0. We will say that it has a potential function which will be defined like this way. V, this is more specific definition to maintain the notational accuracy. We can already see that the potential I am writing, it has x dependence as a variable, and it has a parameter dependency L. That is why they are separated by a semicolon. So what we are saying is that this V would be the defining condition of the potential for the free particle in the box is given by V would be 0 when x, for all x less than equals to 0 to L. So it has to be greater than equals to 0 and less than equals to L, and this is going to be infinite plus infinite otherwise. So this is the definition we are giving. So we are not usually from when the popular quantum chemistry books, they present particle in one dimensional box problem, they directly take this V to be 0. We are also taking V to be 0, but we are explicitly writing down to maintain the notational accuracy. These notations needs to be clearly written to understand this quantum adiabatic theory. Otherwise, things can be little confusing for the for a person who is learning this theory for the first time. So what we are writing is that this is the defining condition of the potential, where the potential is actually 0 inside the box, and outside the box it is the infinite plus infinite. We have included this L term here to maintain the notational accuracy here. In general, this is not done actually in the popular quantum mechanics books, because they assume that L is constant and also V is 0. We directly write it down like that way. The defining condition of the potential term, which I have written here, mandates the fact that the particle remains completely free inside this box. So inside the box it will be completely free. It's a free particle, but is it confined within the box. Outside the box you have potential, infinite potential. That's why this infinite potential, it prevents it, this infinite potential prevents its escape from the box. So the particle cannot go outside the box like this way because of the infinite potential. Now for the demonstration of quantum adiabatic theory using particle in one dimensional box problem, we assume that this L changes as a function of time very slowly. So it is a slowly expanding box, and this slow expansion, this is the adiabatic approximation. That's why it is called adiabatic theory, quantum adiabatic theory. As a result, the defining condition of the potential. So what is L? L is actually controlling the defining condition of the potential. It is the defining condition of the potential, and that defining condition is also changing, because L, if the L is changing, the dimension of the box is changing, so potential, the behavior of the potential is also changing slowly, of course. And because potential is changing, and then if we look at the energy expression for particle in one dimensional box, we see that if L is changing as a function of time, then En, the nth energy state, will also change very slowly. And because if L is increasing, that means for the expanding box, energy is slowly going down for the same nth excited state. For the same nth energy level of the particle. So these are the facts which one can immediately conclude from this expanding box problem, employing this quantum adiabatic theorem, where adiabatic approximation is the slow expansion of the box. Now, here we may assume that the adiabatic process of slow temporal change of length L of the box is turned on. So what we will do, the assumption is that the process of adiabatic change, is turned on at t equals 0. That's the initial time. It was turned on, and then the same thing is turned off at a later time t. T can be anything. I mean, one can choose what kind of t one would like to have. So t has it's an arbitrarily chosen time, later time. So it is turned off at t, and the entire so if it is turned off at t, then what happens, the wave function, the psi n wave function, nth eigenstate wave function of the particle, we said that it has a temporal phase factor e to the power I En t by h cut. It has a temporal phase factor. Now the time, it's evolving from 0 to t time. Because it is evolving from 0 to t time, nth stationary state. So this is the nth stationary state. Nth stationary state. This nth stationary state wave function psi n, due to this adiabatic expansion which is occurring from 0 to t, immediately after the adiabatic process is turned off, I will call this to be at time t, when just I have turned off the adiabatic process and I am trying to find out what is the nature of the nth stationary state of wave function, then that will have an accumulated phase, total accumulated phase, which should be given as exponential of minus I by h cut 0 to t En t dash dt dash. I am just separating this integration variable from its limit. So that's why we have used t dash. So what is the basic idea? Because when this adiabatic change is occurring, the parameter itself is changing. The parameter controls En, and if the parameter is controlling En during the time, this 0 to t time interval during which the adiabatic change is going on, an instantaneous time. So for in this duration, an instantaneous time at instant time t dash, any instantaneous time t dash within this time interval during which the energy En would depend on that time. At that time, at that t dash time, what is my energy? That is defined already by this expression. This is going to be n square pi square h cut square divided by 2m then LT dash square. So at that time what would be the length? That length will decide what would be the energy state for the nth eigenstate, the energy of the nth eigenstate. So and it's evolving from 0 to t, that's why total accumulated phase has to be of this factor is the total accumulated phase. And because this phase is accumulated by the nth stationary state, in the end we can write down the nth stationary state as follows. Nth stationary state is actually the nth stationary state at the at that particular time. So if I consider at t time the adiabatic process has turned off. So this is the time when it is turned off, and this is the time when it was turned on, and any time in between is the t dash time. So at the time immediately after the adiabatic process is turned off, at that time if I try to find out the wave function of the nth eigenstate of the particle, it is going to be this, where I have this total accumulated phase given by this one. So the wave function, each nth eigenstate wave function is accumulating a total temporal phase, and that is given by this expression. Now the overall task, the task of the quantum adiabatic theory is to determine the state of the quantum system, the wave function, immediately after the process of adiabatic length change is turned off. That is, when the box adapts the length LT. So the entire task of quantum adiabatic theorem is to determine the state, which is nothing but the wave function. I need to find out the wave function at this time, the wave function of the system. So psi t, this is what I have to find out. Psi t at time t, immediately after the adiabatic change has been turned off, what is the wave function of the system? What wave function is representing the current system immediately after the adiabatic change is turned off? And we can remind ourselves that we have already seen that for each nth state wave function, that can be expressed, already we have understood, that can be expressed as this L is actually depends on t at that time, that depends on psi n x LT. So it has accumulated some minus I by h cut 0 to t en t dash dt dash. So this much temporal phase it has already accumulated due to the adiabatic change. So each one has accumulated, and we have to understand how to express the final wave function at that time. One may say that the final wave function is given already here. This is not the final wave function. This is each state how it's behaving. We do not know what will happen to the particle after the expansion, whether it will stay in the same state or it will go to some other states, we don't know. So this only information we have is that the state, each available state is accumulating some energy, accumulating the certain temporal phase already. Each state is has accumulated temporal phase, and we have to find out what would be the final wave function, the total wave function of the system. Now this is what we are going to clarify here. When we will just look at the general consequence of a temporal change of an Hamiltonian. Hamiltonian depends on L. So it depends on L because it depends on the V, and V has a parameter which is L. That's why Hamiltonian depends on the parameter. So this is the parameter which is controlling the Hamiltonian. So we are talking about only parametric change, the change in the parameter. So when we are looking at the general consequences of temporal change of an Hamiltonian, before the expansion of the box, let's assume that the particle was in the ground state. So this is the particle which I am showing, and the circle is showing the population. It's the full population I have in the ground state. The circle, the diameter showing what kind of population I have. Let's say diameter is this entire diameter is actually representing population equals 1. So entire population of the particle is on the ground state, and its energy is given here at L equals 0 time. The length is L, L0 we are specifying, and that's why it is in the ground state. Now what ground state of what? Ground state of which Hamiltonian? Hamiltonian H0. Or specifically, if we want to be notationally very correct, then it's going to be H, then X, then parameter L 0. That's the Hamiltonian we have. So at t equals 0, the Hamiltonian would be H0, and for that H0 I will have this equation. So H0 will have psi 0 equals E0 psi 0. Here I am just not mentioning the coordinate space here. All depends on coordinate space as well, except for E. But it has a parameter, so that parameter dependency I am looking at. So before the adiabatic change occurred, it has the from this TDAC I'll be able to get different states, and we are saying that in the ground state it is present, the particle is present in the ground state. Now after the expansion of the box, it may so happen, this is a quite general consequence we are writing, it may so happen that the particle is no longer staying in the ground state anymore. It may so happen the general consequence of this kind of adiabatic, this kind of change, temporal change of Hamiltonian, the temporal change of the parameter which controls the Hamiltonian is following. The particle may not be staying in the ground state anymore. It may so happen that there is a probability or population in the ground state, there is a probability in the excited states like this. And now the diameters are showing, relative diameters are showing what kind of population I have. Then total, this one plus this one plus this one. Total probability is 1, definitely. But now due to this change of Hamiltonian, it is not necessary that it is an adiabatic change. So far we haven't concluded what will happen if it is adiabatic change. We are just saying that if it is a change, then change of the Hamiltonian, then the general consequence is that the particle may not be staying in the ground state, it can go to the excited state as well, and there can be a development of population in states other than the ground state of the final. What is the ground state? Final HT. So for final HT, I will have this TISC, time independence Schrodinger equation, which is this T. This is the final, and we have this N, N, En. Here also we have N, N. So this is the time independent Schrodinger equation at time t, immediately after the adiabatic expansion has started off, and just before the adiabatic expansion was initiated. At that time TISC is given by this. So if I solve this equation, at that time there will be an L. For that L, if I solve it, I will be able to get different energy states, and those energy states may have certain population because of the change, temporal change of the Hamiltonian. This is the very general concept of temporal change of Hamiltonian. Now, when the Hamiltonian of a quantum system changes as a function of time, in principle, the particle which was present in the nth discrete non-degenerate stationary state of initial H0, so this is the Hamiltonian, may undergo the transition, and in that case there can be development of probability of finding the particle in states other than that nth discrete non-degenerate stationary state of final HT. So when I say final HT, more specifically it is actually H, then X, then semicolon L, T. That's the Hamiltonian. So for this particular Hamiltonian, I'll be able to get different states, and it may so happen that these states are populated in a certain way. Thus, the temporal evolution of Hamiltonian creates a non-stationary state of the particle. So it is quite clear that because Hamiltonian is changing as a function of time, the state is a non-stationary state. And non-stationary state of a particle, we know that any non-stationary state of the particle. So in the previous slide we said that we have to find out psi t. This is actually non-stationary state wave function, non-stationary state wave function. The particle can actually be in the non-stationary state after the expansion. It may not be in the stationary state. That's the general consequence of any time evolving system, because the system is evolving in time, and whenever the system is evolving in time, the system cannot stay in the stationary state. These are stationary states. This stationary state, this is a stationary state at time t, which means for a particular length of the box, this is a stationary state. But particle, because of this expansion, because of this possibility of development of the population in different states, the states which is defined by HT now, because of this development of this population, one can say that the particle is not in a stationary state anymore. It is in a non-stationary state, which is defined by psi t. And this non-stationary state, we know that it can be represented as a linear combination of the stationary state at time t. So all the stationary states at that time, whatever I can get, those stationary states I can collect with its corresponding phase factor, and then linearly combine them to get the non-stationary state. This is a very common approach to solve TDSE. How do you solve TDSE? This is something which you should remember, because any time for an unknown system, if we want to solve some dynamical problem, the problem should be viewed like this way. First, and this approach is called Schrodinger's approach. So we will use this approach, very common approach, to solve the dynamical problem. This is called Schrodinger's approach. So what we do here is that first we solve TISE. If I solve the TISE, which means the TISE before the time evolution. So by solving this TISE, I get stationary states of the system before the dynamical event is initiated, which means I can call it is at t equals 0 time. So at t equals 0 or before t equals 0, when the dynamical event is not initiated yet, I have to find out all possible stationary states. Okay. Then after the dynamical events has initiated, once the dynamical event has initiated, then we cannot say that the particle or the system in a stationary state. It is going to be in the non-stationary state, and the non-stationary state is given by psi n x e to the power minus I e n t by h cut. Linear combination of all stationary states with its own phase factor and expansion coefficient. That's the way we get that non-stationary state, and this is called trial wave function. This is called ansatz or trial wave function. This is the wave function which is representing the non-stationary state. But because Cn is unknown, and we know that Cn, the square of absolute value of Cn will give me the population in nth state. A non-stationary state can have several population in different states. So before the dynamical event started, I may have population only on the single state, but during the dynamical the dynamical event, when it's going on, at that time the population, it can occupy different places. It can have population in different levels. I can have population here, but total population is going to be 1, but I can have population development in different states, and that's called non-stationary state. And in order to express that state, I need to know the population, and that population can be obtained by inserting this wave function, trial wave function, to the TDSE. TDSE is equals h psi xt. We have to insert that to get this population, and once we get the population, then what will happen, we will be able to define what is the non-stationary state, this non-stationary state will be defined in terms of stationary states, but I need to know the population, relative population for each stationary state, which is defining the non-stationary state. Now, this is the very general approach to solve any dynamical problem with the help of TDSE. Only difference here is that the same thing is happening here also. We are saying that we started with the ground state, and at t equals 0, it evolved up to t equals t time, and due to this evolution, I may have population in different states. The states are now defined by this HT Hamiltonian, but the overall state, overall physical state of the particle, not quantum state, physical state of the particle is given by now psi t, which is a non-stationary state, which will be expressed in terms of linear combination of the stationary states defined by this HT. So, same idea we are implementing, only difference is that here we have assumed that En does not change. Previously we have assumed, but here in the problem we know that En is changing as a function of time. So, the total accumulated phase cannot be just e to the power this, but e to the power exponential of minus I by h cut 0 to t En t dash dt dash. That's going to be the total phase accumulated by the nth stationary state of HT. So, with this consensus, we will move on and we will look at the problem which we have, the non-stationary state of the particle. So, basically what we are doing here, before expansion of the box, the particle is in stationary state, and the state is defined by the Hamiltonian H0. But after the expansion of the box, the state is not a stationary state anymore. The particle is in non-stationary state. So, I have to express it like this way, and that non-stationary state we have said that following Schrodinger's approach can be expressed in terms of linear combination of CNT, then psi nt, then e to the power minus I by h cut total accumulated phase up to time t En t dash dt dash. That's going to be the non-stationary state at this time, immediately after the expansion has is over. So, one key point which you should remember, that before the expansion definitely particle was in the stationary state. Here we are assuming that it was in ground state, that's why the stationary state can be defined as psi 1. In the psi 1 stationary state it was there. But after the expansion, because the Hamiltonian has evolved over the time, it's a dynamical event, the particle has to be in the non-stationary state. Particle cannot be in the stationary state. Immediately after the entire change is turned off, immediately after that. And that non-stationary state will be defined with the help of the stationary states at that time. And the stationary states at that time will be defined by HT. That's the stationary state. So, those stationary states I have to collect and then plug that in here. So, these stationary states are obtained like this way, E T n psi n t. So, this is the wave function which is representing the stationary state at that time, and this stationary state we have given, and the contribution of each stationary state is given by this expansion coefficient, the contribution to the total non-stationary state. So the key information here we should remember that non-stationary state is prepared actually after the expansion. We will continue this session in the next class.